So chapter 23, number 19 says, so in this one it tells us we have three charges, right? Always drawing a diagram is a good idea. There's a charge of plus 2q in this at the origin, and minus q along the x-axis. And it says it's a distance d away from the origin, so we'll label that. And then we want to find a symbolic expression. That means we don't need a number. We're just looking for an equation for the net force on a third point charge that's also plus q located along the y-axis at d. So now we've got another one here, also a distance d away from the origin but along the y-axis. This one's also plus q. And we want to find the force on this one here, right? So this is our test charge, really, and these two are our source charges. So we'll use superposition, right? That's the plan. We need to find the force on this charge from here, from the one on the origin, and we need to find the force on this charge from here, from the one at the minus q, right? And then we add them together. All right. So what's the force on this charge? Well, we use superposition, so we know that the electric force that we're looking for is going to be the force on it from, let's call this one charge A over here, and this one charge B. So it's going to be the force from charge A plus the force from charge B. So from charge A, right now let me write out Coulomb's law just as the general form so that we can refer to it. And I'll use, we should get used to going back and forth between k and 1 over 4 pi epsilon naught, so I'll use k today. Right, so there's Coulomb's law just for reference. So for the first part, charge A, right, or point A, we have K. So the Q1, the source charge, is positive 2Q. Q2, the test charge, that's just positive Q. My R squared, the distance from this charge to that charge, should be pretty clear, right? That's just D. So D squared there. And then what's the direction of this vector RA? How would I write this vector?
J hat?
That's negative j hat. Is it negative j hat or is it positive
j hat because you're going up.
Okay.
For that one, for that R vector, it's always from the source charge to the test charge, right? So we point from the charge that's exerting the force to the charge that's feeling the force. So it is going to be a positive j hat. Right, so that one's the more straightforward one. Now we have to add to that the force from this charge. All right, so again, we use Coulomb's law. All right, we get K. So this time our source charge is not 2Q, but it's negative Q. The second charge, our test charge, is positive Q. Okay, now I need the distance, right? I need how far, just the distance from this charge to that charge. What would that distance be?
Say again, sorry.
How far?
Square root of d.
Of 2. Square root of t, 2 times d.
Yeah, square root of 2d.
Right. We know that this distance here, just because it's a 45, 45, 90 right triangle, right? This distance is, square root of 2d, right? Anybody disagree with that or not sure how?
No, I agree.
Me too. Okay, so we still need to square that, right? If we're putting r squared.
That's just 2.
2, yeah. So if we square that, we get 2
d.
Not quite. Almost there.
2d squared.
D squared, right? Only the 2 is square rooted here, right? When we square that, right? Square root of 2d all squared is 2d squared. Okay with that?
Yes.
And now the trickiest part is figuring out what this RB is going to be, right? What's this vector, or the direction of this vector? And it's not along I hat or along J hat necessarily, right? But we do know this RB is going to be equal to cosine of the angle of B times I hat plus the sine of the angle B times J hat, right? We can always replace our unit vector with this form. So we just need to know what angle B here makes with the positive x-axis. Can anybody tell me?
45
degrees.
I heard 35.
45
degrees.
Almost. That's good thinking. But we want to be careful, right? If we use 45, we're going to have a minus sign somewhere in the wrong place. We always want to make sure this angle, when we're referring to it, is the angle that we make with the positive x-axis. So really,
Oh, so 135.
Oh, 135.
I want to use this, right?
135.
135 is what we want to plug in, right? And that's not going to make a difference for the cosine, but it will for the sine. Or I might have said that backwards. But yeah, theta B, we can see if, and that's why it helps a lot to draw out diagrams and actually draw the angles in and draw the positive x-axis. Theta B is 135 degrees. So that gives us, if you plug into your calculator or if you know your unit circle real well, we're going to get the cosine of 135 degrees should be minus root 2 over 2. And you can check and make sure I'm right about this. I think it is. Plus, and then the sine of 135 degrees, we should get just positive root 2 over 2. Does that make sense?
You said the sine or cosine? Oh, wait, my bad.
I'm saying, and you might want to confirm this because I haven't checked it lately, cosine of 135 degrees is minus root 2 over 2.
You are correct in both.
All right. Sine of 135 degrees is positive root 2 over 2.
Mr. Ali's waiting for you to let him in.
Oh, thank you. Yeah, I got you. Thanks for reminding me. So what I would do now is over here, I'm going to put what I have here, right? Minus, and I didn't leave a lot of room, times minus root 2 over 2 I hat plus root 2 over 2 J hat. Yeah, I think you can see that, right? So that's basically what we have now. Now, you know, this expression here is going to be our answer. We just need to simplify this down a little bit. And sorry to keep you waiting, Ellie. Okay. So let's see, how can we simplify this? So why don't we factor out the K? There's a capital Q squared in both terms, and there's a D squared in the denominator in both terms. And then in the first term, I have left just 2J hat. And then in the second term, I have a minus, and then this 2 in the denominator is minus 1/2 times a minus root 2 over 2 I hat plus root 2 over 2 J hat. So now now I want to group together my I hats and my J hats, and that should be all I need to do. And stop me if I'm going too fast or if I miss something. So let's see, in the I hat, we have -1/2 times negative root 2 over 2, which is root 2 over 4. And then for the J hat, we have 2 minus 1/2 of root 2 over 2. So I think we just have 2 minus root 2 over 4 J hat. And I think that's about, I mean, I guess we could factor another 2 out of the, no, maybe not. We can just leave it as this. I think it's about as simplified as we need to get it. That's where I would leave it anyway and say that's my answer. Is there any questions about how I simplified it down to that, or maybe I made a mistake? I don't think I did. But this is kind of the first time you want to get used to having, this is a symbolic expression, right? This is an equation as our answer. We don't have any numbers to plug in beyond this.
What I'm confused about is, isn't like two positive charges repel each other? So why isn't like the force basically, how to say it? Why isn't it like negative for the two positive charges on the right?
Okay, so let's see. Yeah,
Sorry, on the left.
So, well, if we look at this, right, root 2 over 4 I hat, so it's going to be a positive direction in the I hat, right? So this force is going to feel some force to the right. And in the J hat direction, it's 2 minus root 2 over 4. That's still a positive number, right? So we still have a positive of the forces in the positive J hat direction, right? So the net force is going to be, up and to the right. It won't be exactly at a 45-degree angle, but it is being repelled from these, right? It is being forced in the upwards direction from both of these put together, right? This one tends to pull it down towards it, but this one pushes it upwards away, right? And since this one has twice as much charge and it's actually closer to the test charge, this one wins out, and this one does feel an upwards force. And both of these charges tend to push this to the right, right? This one is, well, at least once it starts to move to the right, it's going to be pushed away farther and farther from this one. Does that answer your question at all? The answer is, yeah, it is repelled by this charge, right? The net force is an upwards force and a rightwards force.
I see.
And that's a good point. You do want to, check and take a look at the force and see that the direction it's being pushed makes sense with what the charges are.